Good day, everybody. Good morning, good afternoon. Welcome to the backyard again. Today's lesson is going to be on calculating cell potential. All right, so this is the third lesson actually on this topic. So if you remember, we started out by balancing redox equation. We then assigned oxidation numbers. And now we're going to calculate the voltage that is generated by galvanic cells. So we're going to begin. As you see here on my share screen, I have your notes that are opened up. Chapter 18, section 18.2. So I'm going to use this mostly for a review of what we've been talking about, and then we're going to jump into the calculating the potential. So open up, pause the video, open up your notes. The other thing you're going to need is this sheet right here, the standard reduction potentials, and this is also available in your OneNote. So you'll need both of those things. You might want to print out the standard reduction so you don't have to flip back and forth. Okay, 18.2. Galvanic cells. So we recall Leo the line goes GER, which was to help us remember that when a substance loses electron, it's the oxidation process, and when there's a gain of electron, that's the reduction process. So there's a cell right there, well, part of a cell that is. On the one side you have the MnO4, on the other side you have the iron. And then this is a description of the reaction that's taking place. So the idea when we do this, right, is that we have an oxidation and a reduction. So we have one half of the reaction that's going to lose electrons. We have the other half of the reaction that's going to gain electrons. So what we want to do is to channel these electrons from one half to the other half. So using a wire. And so this channel of electrons, it is going to carry some energy, and that's what we're going to talk about today. So we're basically going to harness the energy of the electrons as they're going by. So that's the whole idea behind the chemical cell. So if we're doing this here, we're looking at this reaction. We see the two halves, they're in separate beakers, and what we're going to do is determine the oxidation half and the reduction half in this process. Recall when we were balancing redox, the H pluses and the H2Os, they're only added there to make everything balance out, right? We were adding the H plus to balance the H's, we were adding H2Os to balance the O's. So we're not going to really mess with this. They're just there. It's just adding clutter to the whole thing right now. So if we're looking at MnO4 minus, that half reaction, right, that substance is turning into Mn2 plus. So here's one half, and then the iron 2 plus going to iron 3 plus. There's the other half. Oxidation numbers, well, for the iron half, it's pretty easy because it goes from 2 plus to 3 plus. And so what we're seeing here is that the iron 2 plus lost an electron and it turned into iron 3 plus. So losing electron is the oxidation. So the oxidation reaction, as it is here, is the 5Fe two plus going to 5Fe 3 plus. And of course, there's going to be 5 electrons that are produced. So since this is the oxidation half reaction, the iron 2 plus is being oxidized. So another way of looking at it is, if it's being oxidized, it causes the reduction of the other one, right? The substance that's being oxidized is the substance that loses the electron, which causes the other substance to gain electron. So the substance that's being oxidized is the reducing agent, what causes the reducing of the other. And likewise, the one that's being, well, we're going to talk about the MnO4, but so Fe2 plus is oxidized, so it is the reducing agent. The other reaction is the MnO4 minus turning into Mn2 plus. And so here, well, to balance it out, we would put the plus 4H2O, and then on the other side, the 8H plus. But what we're focusing on here is the MnO4 minus to Mn2 plus. MnO4, so the oxidation number on the oxygen is 2 minus, if you remember the rules from last week. So this oxygen is 2 minus, and there are 4 of them, so that's a total of 8 minus. If the overall MnO4 is 1 minus, that means the Mn is 7 plus. So Mn goes from 7 plus to 2 plus. So it has to gain 5 electrons. So there's 5 electrons that are on the left of this reaction here. MnO4 minus is being reduced. So it causes the oxidation. So the oxidizing agent is MnO4 minus. Right? So again, here's how it goes. The substance that undergoes reduction is the oxidizing agent, because by being reduced, it causes the oxidation of the other substance. The oxidation half reaction, the substance that's being oxidized, causes the reduction of the other substance. So the substance being oxidized is the reducing agent. So there's a transfer of 5 electrons in this process, and that's what would go through the wire. So the substance that's losing the electron is the iron 2 plus. The iron 2 plus is over here, right? And so you're going to get 5 electrons that are going to flow this way. It's going to go from the iron, and the MnO4 receives the electron. So this is the oxidation half right here, and this is the reduction half right there. Now this reaction wouldn't proceed because it's not a closed circuit, right? And you've learned in physics that in order for the electricity to flow, the circuit needs to be closed. So there needs to be a return here. There needs to be something that's gonna be bringing back the charge equilibrium. This is what's caused, this is the purpose of the salt bridge. So the salt bridge, if you look on this second diagram, there's a salt bridge right there. So that's what it is. And that's where the anions are going to be moving from one side to the other to rebalance the charges between the two sides. So this is what a galvanic cell, bare bones, would look like. You have the half reaction in one beaker on one side. You have the other half reaction on the other side. You have the wire that will conduct the electrons from one side to the other. and you have the salt bridge that will bring everything back, the charges back to balance out. Our job today is to calculate the voltage of such a cell. A galvanic cell, as opposed to an electrolytic cell, we're going to come back to that topic a little bit later, but the galvanic cell is spontaneous. And what that means for us in redox is that the voltage will be positive. So a galvanic cell, right, we're always looking for a positive voltage. In other words, this cell happens by itself. It's spontaneous, right? An electrolytic cell is one that requires a power source to proceed because the potential difference, the voltage, is going to be negative. So it's going to need an input of energy to proceed. So an electrolytic cell could be used, for example, when you're plating metals. Right? If you have an object and you want to deposit a gold layer, so gold plating or silver plating or something like that, that's what an electrolytic cell would be used for. So what we're going to focus on in this lesson is always generating a positive voltage, and that will be a galvanic cell. This is going to be very important to determine which side is the anode and which side is the cathode. So that's what the cell potential is. Right? The cell potential is what we're calculating today, is the voltage. It is, if you will, a pressure, an electron pressure. You can look at the voltage or cell potential like that. How much pressure are the electrons subjected to? What is the pull or the push on the electrons in this wire? Now be careful though, because the pressure doesn't exactly correlate to how many or how much electrons are going by per unit of time, because that's current. Here we're just talking about the pressure that is exerted on the electrons, or the pull or the push, right? But remember, there's also another factor that would limit the flow, which is the current. The other factor that would limit the flow is the resistance. Like you may have a huge pressure, you may have a huge voltage that's pushing the electrons one way, but if the conduit has a very high resistance, then there isn't going to be much flow. So pressure is not equal to flow, right? Because there's the third factor, which is resistance. So what we're talking about here is the voltage, which is the pressure. So this is referred to as the electromotive force, or EMF, and it is measured in volts. Okay, so let's go to section 18.3, standard reduction, calculating that. So here's a much nicer diagram of the cell. And so we see here we have a zinc electrode, so the solid zinc. And we have a zinc nitrate solution. So this is in zinc 2+. Right, so zinc 2+. And on the other side, we have the copper electrode, which is Cu, and this is in a solution of copper 2+ ions. So you have one reaction is between, half reaction is between the copper and the copper 2+, and the other half is the zinc and the zinc 2+. So a few things to help us remember what's occurring where. So we know Leo the lion goes Gur, right? And that's to help us with oxidation and reduction. And here we're going to think about red cat. And so red cat tells us that the reduction occurs at the cathode. So reduction occurs at the cathode. And remember, reduction is GER, gain electron reduction. So electrons are gained at the cathode. I'm in trouble with my pen. How to determine which side gains the electron and which side loses the electron. So this is where we're going to use our standard reduction potential table. This one, right? You print it out. So it's also in your notes. It's over here. So here's how we're going to do this. Let's look at this example here that we have. Example 1831. So we see this reaction, Al3 plus, and on the other side is Al. And we have magnesium to magnesium 2 plus. So these are our two half reactions. Right. So what we need to do is we're going to need to have the balance cell, and we're going to calculate the E0. This is the cell potential, and this is a voltage that's generated. Okay. Now, as it is written there, we have Al3 plus going to Al, and this is going to require 3 electrons to balance out the charge. The other half is magnesium, becomes magnesium 2 plus, and here we're going to have to add 2 electrons to balance out the charge. Now we have to look at the cell potential table, and we're going to locate these two half reactions. So Al3 plus 3 electrons gives Al. So if we look at the chart and we find this reaction right here, Al3 plus 3 electrons, so negative 1.66. Negative 1.66 volts. The other reaction is the magnesium 2 plus 2 electrons. So we're going to find that reaction right here. Magnesium 2 plus 2 electrons is negative 2.37. But notice here on this is a reduction table, right, where the electrons are being gained, gain electron reduction. So this process, the reduction process, is negative 2.37. What we have is the oxidation process. So it's the reverse reaction. So we're not going to have a negative 2.37. We're going to have a positive 2.37. So when you look at the table, this is a table of reduction potential. So all of the equations that are written down on this table are written in the reduction form. If you're using the oxidation form, it's the same equation, it's just backwards. So you just change the sign on the voltage. So negative 2.37 for the reduction is positive 2.37 for the oxidation. And all we have to do is to add the two halves, and this is going to give us the overall voltage of the cell. Remember that because this is galvanic cells, the voltage always has to be positive. So in this case, it's perfectly written because the greater number, right, is positive. But we're going to see in an example just a little bit down the road that sometimes you have to flip things over. All right, so negative 1.66 plus 2.37, so that gives us a positive 0.71 volts. So that's the voltage. And they want the balanced equation, which means that we have to make sure that the electrons that are being gained are equal to the electrons that are being lost. So that means that we're going to have to multiply by 3 and multiply by 2. And that way, 6 electrons will be gained in the reduction, and 6 electrons will be lost at the oxidation. So the process is going to be then 2 Al3 plus 3 Mg gives 3 Mg2 plus 2 Al. So this is the balance equation, and that's the voltage. So what I would like us to do is to practice this some more. And to do that, we're going to open up your homework or worksheet. Let's see. And we're going to look at the first problem that you have on this worksheet, which is to calculate the cell potential that is produced by a galvanic cell, where you have a nickel electrode in a nickel 2 plus solution and a silver electrode in a silver plus ions. So how we would, the notation, there's a shorthand notation for these cells, right, where we would put 1/2 reaction, so that one of the halves is from nickel to nickel 2 plus, and then a double line. On the other half of the reaction, it would be silver and silver plus. So this is the shorthand way of representing cells. So what we're going to do is we're going to write down both of those equations. So I'm just going to move us over to the side here. Nickel gives nickel 2 plus, and silver gives silver plus. Actually, let's write those as reductions so that it's easier, so we can identify them on the sheet. So nickel 2 plus 2 electrons gives nickel. And silver plus 1 electron gives silver. So we're going to go back to our cell potential, a reduction potential sheet. And we're going to find these two half reactions. So the nickel 2 plus 2 electron that gives nickel is a negative 0.23. So negative 0.23 volts. And then going to the silver, is not very reactive, right? So it's going to be higher on the sheet right here. So silver plus 1 electron gives silver positive 0.80. So as it is written here, it is positive 0.80 volts. So we always want the galvanic cell to have a positive overall output, which means that this has to stay, the silver half has to stay the way it is. It has to be the reduction. So we're going to keep this as a reduction. Remember, gain electron reduction. So the silver plus is gaining an electron. So this is the reduction. Going back to a couple minutes ago, the silver plus is therefore the oxidizing agent, right? It's being reduced, so it causes the oxidation. The other reaction will have to be the oxidation. So the nickel half will have to be the oxidation. So what we're going to do is we're going to write the nickel half in the oxidation form. And this negative 23 is going to become positive 23. So now we have the oxidation. And we have the reduction. The voltage is just the sum of the two. So positive 1.05 volts is going to be the voltage. The overall reaction is going to be, we're going to have to multiply the silver half by 2 for the electrons to be equal. Right? So the overall reaction is going to be nickel plus 2 silver plus gives nickel 2 plus 2 silver. Which is the anode, which is the cathode? Well, we remember red cat, the reduction occurs at the cathode. So the silver electrode is the cathode, and the nickel electrode is the anode. The electrons always flow from anode to cathode, A to C, always. So the electrons start at the anode, right? The nickel gives 2 electrons. So these 2 electrons travel in the wire to the other side, and the silver plus picks up these electrons and turns into silver. Always the electrons travel from A to C, anode to cathode. And that's how you do these problems. So I wish you guys a great day. This does require some practice. So have a great rest of your day, and I'm looking forward to seeing you again next time. So thank you very much.